next and last group of speakers. They are from EPAM System. We will have the pleasure today to welcome Uladislaw Bayuski, Konstantin Barabanov, Maxim Dzvik, and Vasily Slapik.
My name is Konstantin. I will start. So I'm senior delivery manager with EPAM Systems, working there like 12 years, and also all of us, we are part of IoT community in the company. And we would let you to present what we are going to present today. And let me pass this to Maxim.
Yep.
Hi everyone, my name is Maxim, so I'm a lead electromechanical engineer and I'm responsible of the hardware as well here at EPAM Made Real Lab, where we build awesome and sometimes even incredible prototypes, alpha devices and preparing devices for mass production later. So the focus of Main Real Lab is to assist our huge software department to deliver cutting the edge and up and coming devices that you often can see on the shelf of the store or somewhere uses in their daily life. Nice to meet you all.
Hello, nice to meet you all. My name is Vasily Slapik. I'm within EPAM for like 14 years already, and I'm a chief software engineer at EPAM, and my primary specialization is devices firmware, device drivers, low-level programming, basically inflating life in hardware with help of software and firmware. This is what I'm doing.
My name is Vladislav Bayovsky. I'm Senior Director of Engineering. And as I mentioned, thank you so much for that opportunity. And we say hi from sunny California. And today, definitely, we would like to join the audience and the colleagues who already presented different topics and shared different experiences from technology point of view, product point of view. And talk about how we can make agriculture, how we make agriculture smarter. We already did this introduction, but just to highlight on the colleagues, we have also Konstantin Barabanov, Senior Delivery Manager, Maxim Dzvik, Lead Electrical Mechanical Engineer, and Vasily Slapik, our Chief Software Engineer. Technically, on the video on the screen, you see the promotion materials about Made Real Lab. So we work in EPAM Systems, and EPAM Systems is a global IT service provider and technical consultant company. We have offices in various locations. So we understand that the IoT is definitely a huge area and very important area which affects a variety of industries, right? And we try to bring awareness to IoT through different options, different ways. We do have like garage approach where people mostly focus on pure hardware prototyping. We do various communities where we try to involve people in a simple, without any commitments way, try to gamify the way they learn and get more information from different sources. And we do have our, let's say, global practice we call Made Real Lab. And Made Real Lab is focused on end-to-end prototyping of different products. And some projects we share today were designed and fully kind of like completed, assembled in Made Real Lab. So technically, to imagine like the capacity and possibilities of Made Real Lab, we do have multiple locations like Boston in the United States, Poland, Hungary, and usually they have huge facilities, like huge space to build products, because it's not always about some tiny devices. Sometimes it's about real attempt to make a full copy of the product on a bigger scale. The thing is that through the different approaches, like as I mentioned, garage communities and the Made Real app, we definitely want to focus as well on areas which bring additional value to people, to the society. I would like to give a couple examples of projects we were either working on or consider them as prototypes or proof of concepts. So the first one is about the complete solution. And when I say complete, it's about involving multiple areas where we could use our expertise and knowledge to build a solution. So it was a complete solution about involving multiple sensors, drones for monitoring, and the application itself, which was a complete dashboard to monitor and to manage the data which was collected and aggregated from multiple sources. So the data which we got was different statistics related to soil, to weather forecast. So technically, when drone was used to monitor the crops, the fields, because of collected images, pictures, and the AI machine learning analysis, we could better identify areas where we experience issues with crops for some reasons, and to identify the issue on early stage. So technically, it could be related to some pests, maybe wrong conditions of soil, maybe incorrect usage of different stuff and chemicals, whatever. So the best description of this project was early detection of potential issues and problems. The next slide, it's more about software approach. The thing is, we do have in United States and in Europe, there are different publicly available sources of agriculture-related data. The issue is that in most cases, these sources, they use different formats. So it could be well-known, easy to use, easy to transform, JSON, XML, but at the same time, it could be some kind of proprietary binary formats. And definitely, if you would like to aggregate them all to extract, transform, collect this data, you face with a very, very potential and actually real issue. You need kind of to have multiple solutions to process all this data. So the idea was to build a solution which follows FAIR principles and gather all possible data sources to aggregate this agriculture data. The idea was to use it later for data models training, because if you're familiar, and today most of people who are involved in the technology sector, they are familiar with definitely machine learning. You know that data model is fine. I mean, development of data model is challenge at some point, but training data model is even bigger challenge because you need to collect this data, to label this data properly. So that solution was actually used to create the way of aggregation of this data. And eventually, as I mentioned, based on FAIR principles, it was possible to use these multiple data sources and to fully automate the pipeline. So technically, with different approaches such as web crawlers, all this data was gathered on a schedule. Then it was passed through transformation pipelines, and eventually you get JSON linked data information in JSON linked data format, which is easy to use, to read, and to actually share with any other solutions, products, APIs, whatever. So that's just a brief overview. As I mentioned, we go into mention more products, and now I would like to pass the microphone to our lead electromechanical engineer, Maxim Zvig. Maxim, the microphone is yours. Thank you so much.
Yeah, thank you very much. And once again, hi everyone. So just to continue on our discussion, we're all aware that nowadays agriculture requires smart and digital solutions. And one of the steps to make it efficient is generally to automate monitoring process. Get data about soil, air, and plants parameters in real time, and this will allow you to make the predictions. Just imagine, for example, reforestation or crops monitoring. That could be hard to reach locations or area without or with lack of internet coverage. We should minimize our manual labor or field work, and we should try to minimize it as well. So we challenged ourselves how to solve these puzzles, how to transmit data without internet coverage, how to make solutions self-sustainable with energy harvesting. We brought the whole team of different experts and decided to prototype that solutions. So a soil moisture and the air temperature sensors with the processing unit as the LoPi4 is an IoT platform. And we're using long-range LoRa radio protocol to send data without internet connection to a remote gateway that's connected to the internet and delivers data further to the cloud. Device has energy harvesting, accumulates solar power, and that allows us to be self-sustainable. We assume that the future of agriculture is digital, and we already prototyping that with EPAM Madrigal Lab. So let's slightly talk about the overall solution overview. So generally, this is a compact field device made up with soil and air sensors, CPU board, solar panel, battery, and this whole device just gathers data. After gathering the data, this data is processed locally and prepared for transmission. LoRa or long-range radio modem transmits this data to the gateway, and this gateway can be located up to 12 kilometers away. So next, accumulated data from several devices. Of course, we are assuming that we're using a cloud of different nodes or devices that are sending the data exactly on the same gateway. And after that is sent it to the cloud. And we're using Microsoft Azure IoT Hub. After that, through the GSM network, this gateway sends data for further analysis and post-processing. Pretty simple, straightforward, and at the same time reliable solution. What about the hardware that we used? And as I'm the hardware engineer, I'm mostly interested personally in the hardware, what we are using to build that. Of course, it's the sensor module to monitor moisture and temperature of the soil itself, and several environmental condition sensors, also temperature, humidity. Recharging battery with solar panel. That allows us to make the device self-sustainable. LoPi4 unit that consists of Espressif ASP32 as the main controlling unit, and Semtech long-range low-power transceiver that acts like that actually a long-range modem, LoRa modem. So long-range wireless network parameters, including gathering and transmitting data, and we set up this frequency not less than once in every 5 minutes, and we easily can adjust it. We're utilizing adaptive data rate, but generally operating at 868 megahertz band. And overall, this device belongs to class A with inactive data receive functionality. So we're just transmitting the data. Whole infrastructure is powered by the ChirpStark open software. And this software allows us to utilize radio frequency management, sensor management, LoRa gateways management, and moreover, facilitates transfer of whole data to the Azure Service Hub. And I think that's it about the LoRa project that we've made with our teammates, and giving word to the next presenter. Thank you very much.
Headliner of our story is Smart Greenhouse project. It was born not from the executive directives of top management. It was like kind of genuine concern for global issues and internal initiative. And we were thinking about world hunger and sustainability challenges like facing modern agriculture. So, and team behind it was driven by shared vision to address these concerns using ESG framework. So in its core, it's like this project is a kind of creative mix of environmental stewardship, social responsibility, and robust governance. Our goal was simple, but quite ambitious. We wanted to create a cost-effective and community-driven innovative greenhouse to improve influence on the agricultural sector. And we were thinking holistically. It was not just about using technology to improve gains and yields. It was about creating a safer, more reliable and sustainable environment to farming environment that could address some of the most pressing issues faced by those who are employed in the sector. And so by focusing on workers' well-being and health of the environment itself, we aim to contribute positively to the communities it would serve. And our project quickly evolved beyond its initial concept, and we decided to contribute to larger community. And as we were gaining momentum, this project got attention for its low-cost solutions. And those solutions promise to minimize the common errors found in non-automated greenhouse, like automated greenhouses, like overwatering or inadequate temperature controls and such. So our greenhouse has a set of features like light and watering control, as you see on your screen, temperature, humidity monitoring, automatic management, automatic photography of plant growth, protection against electricity outages and short circuits. And for sure, we have smart monitoring via internet, via web. So most of these features are very cheap and easy to implement. And also because of that, smart greenhouse represents a leap towards precision agriculture. So technology was just the beginning. Over the course of the design and implementation, the team learned a lot, and we collected a huge set of best practices. This would allow us to continually improving and help us to adopt the system. And by doing so, we think we just set the stage for more sophisticated and even more intelligent solutions. And these solutions may attract the attention of governments, large corporations, and what we hope the most, enthusiasts to foster a new wave of innovation in the agricultural sector. Sometimes engineers do things because they can. Sometimes we do things just for fun. I won't deny it was a fun project, and as engineers, we also know how technology transforms the environment and global ecosystem. Something acceptable 20, 30, like probably 50 years ago is no longer acceptable now. So, okay, our greenhouse is smart. Does it bring any better for environment? Yes, we think it does. First of all, IoT-enabled greenhouses can precisely control water, nutrients, and energy use, and that leads to significant conservation of these resources and reducing waste. Second, we monitor real-time conditions like temperature, humidity, soil pH, so that we can create ideal environment for plant growth and improve yields and plant health. We also can detect pests and diseases early with computer vision and other technologies, and that minimizes the overall use of pesticides and herbicides and other chemicals. And overall, this leads to less contamination. And also, like, environmental conditions are often changing and sometimes to extreme levels. And IoT greenhouses can automatically protect plants from extreme weather conditions and reduce risk of crop failure. And also we collect data through analysis and like analysis helps us allow us to refine agricultural practices continually. And that leads to sustainable cultivation methods that can be shared and replicated in other farming systems, basically. And I'm talking not about only data we collect from sensors. It might be also that most effective hardware and software configurations tied to specific needs might be also collected and distributed amongst enthusiasts. So that's overall description. And before passing a virtual talking stick to a brilliant engineer who contributed to the project heavily and hands-on, we want to thank Java. It's very popular in software development and IoT, and it also helped us to get Oracle Award for the Smart Greenhouse project. So thanks Java again. And now it's time for deeper details about the greenhouse. Please welcome Vasily Slapik to the stage.
Thank you, Konstantin. Being part of the engineering team, I wanted to provide a bit more details about the architecture and the components I've used. But first of all, what about greenhouse? So greenhouse is about growing plants, and here at EPAM we like to play with technologies, and we wanted to see how, with help of technologies, we can make the greenhouse smarter. Smarter means using more precise monitoring, more precise actuations, altering the environment inside greenhouse to make the process of growing is more effective. More effective means spending less water and nutrients and giving more yield. So first of all, we needed to build some isolated environment for experiments. And as you saw on the video on the previous slide, we just made a box from acrylic glass. So we could start growing something inside that box and put our sensor inside the box, and we could put the rest outside. So the most important sensor we had was temperature and humidity sensor. And alter humidity, we used automatic watering mechanism. We also had lamp, so we were able to switch on and off the lamp according to some schedule. We had some air management system, basically fan to move the air. And of course, we had some central computing board where all the sensors were connected. We could run our software, and this computer was connected to Wi-Fi, so we had remote access. last thing is power management for all these components. Here we have some challenges because of water and voltage, they don't mix well. We used so we use approach like it was prototype style, but for real greenhouse, of course, something more sophisticated would be needed. As Konstantin mentioned, we wanted to try to spend not much of money on this project, so we literally built everything from existing components, from very cheap DUI components, and we wanted to reuse as much as we can for hardware and for software as well. So, so the list of sensors and components probably is well known, well recognized by DUI enthusiasts. So we used Raspberry Pi for single board computer. We used digital temperature and humidity sensors from Arduino DUI like DHT11. We used existing relay modules. We reused water pump from old car, and basically everything we bought. Nothing we built from scratch. We just bought all this stuff and connected. So yeah, here are the pictures of some components we used. Like we used water pump, for instance, from some old car like this on the screen. You can spend just $10 and you get your watering management system. The power supply, you also don't need to build it from scratch. You can buy it. Humidity, temperature sensor, soil moisture sensor, all from DI says. And we did have a circuit breaker just in case, but that's probably was the only thing for protection. As I mentioned, it's not mature approach, but we built kind of prototype, not the final solution, so it was enough for us for most of the time. As for central computing unit, we used Raspberry Pi. It's very known single board computer used by DUI enthusiasts over the world. It's very cheap, and it is a size of credit card, so it's really small, and it has immense computing power. It is sufficient to perform way more sophisticated things than serving the greenhouse. So we had a lot of room here for running any software we want, and you never hit the limit of computational resources on Raspberry Pi. It's also very configurable. You can connect any sensors, any peripheral devices easily, and again, you need some configurations, but you don't need to write much of software for interacting with external components. Last but not least, that this is open source driven. The operating system, drivers, some system services, everything is ready for be reused, and also you can improve them and share with a community back. So it was also a big selling point for us to switch to use Raspberry Pi. Again, as Konstantin mentioned, the software which served the greenhouse was implemented in Java, and Oracle recognized that we were winners of IoT Challenge. But some people may ask whether it was easy to integrate Java and force it to work with some sensors, kind of low stuff, low programming stuff. Yeah, on Linux it was easy because Linux is a typical Unix operating system. So all the sensors, all the peripheral devices represented as files, and Java doesn't have any issues with reading sensors well as through the files, through the file system abstraction. So that was not a challenge. However, we do have some issue with one of sensors, and we did have to implement some wrappers, so-called GNI wrappers, Java native interface wrappers, to integrate the driver software into the Java. But that was, I'd say, minor effort, and Java on Linux for Green Smart House it worked well, so not much to code. So in the end, we built the final prototype. We managed to grow beans. We managed to kind of see how beans react to different schedules of watering, how you need to switch on and off the lamp to grow them more effectively. And we saw that indeed it can be rather cheap solution, and a lot of things can be reused. So you don't need to build something very sophisticated. You don't need to build custom hardware and write a lot of software. There are a lot of different components you can reuse, and you can spend very little money to implement a smart greenhouse and achieve many environmental goals, and also share your result with broader communities, so other people may find the right profile to grow something different, not beans. It was very interesting, challenging project, and yeah, I think that's all I wanted to share with you.
Thank
Thank you so much, Vasily. Thank you. Yeah, that's it from us. Yeah, if you do have any questions, definitely we're welcome to address if we can. And thank you again for that opportunity.
Thank you very much. Yeah, we have a question here.
Thank you very much for your presentation, which is very interesting. You emphasize the greenhouse aspect. Do you have any other external application where you use this kind of approach, integrating sensors in a local network using, as you said, LoRa, using a Raspberry Pi in order to control everything? Do you have a digital form somewhere, an external one?
Thank you for the question. So if I got it correctly, you ask about like if we do have an example of integration of all these examples of different technologies into one real like farm, smart farm or smart greenhouse.
Yes.
Okay, so today I would say no, because the thing is we usually work we do our work in two directions. One is when we do invest on our own, when we consider some technology, some idea could be promising or could be helpful in terms of, as we mentioned, like CSR involvement. The other is when we do have a project request from our customers. So technically on the, let's say, prototype level, on the overall idea level, yes, we do have such solutions in mind where we could combine all these technologies and products we were working on. But you're absolutely right in terms of the main idea of all these projects we shared. And in general, Major Lab we have is to have all the available components And in case we have an opportunity or demand to build something like as a complete real smart farm, we do have all these components ready. So we just could assemble them as a Lego.
Okay. Okay, thank you. And then, sorry, and then there will be other question near to me, but question concerning the storage of data. It seems in a certain point that you use the cloud from Microsoft, Azure Microsoft, and do you have any strategy concerning creation of kind of data lake with the data coming from captors, from different device, and trying to analyze using AI tool, for instance, to detect diseases or anomalies in the crop? So do you use, for instance, artificial intelligence tools for that, or what kind of approach do you have in the present or in the future concerning this kind of image analysis you taking? So first question concerning the storage itself, what kind of DBMS are you using? Do you use NoSQL database, or for instance to store the data in the cloud, or and then what kind of AI tool you using for image analysis?
Okay, got it. So, Maxim, do you have information about LoRa in terms of cloud and data management for LoRa?
Of course, I have lots of this information. I would like to highlight that I'm mostly a hardware guy. I'm the guy who builds the hardware. So I can send all of this data about a bit later. I mean, with stating how we're using this cloud, Microsoft Azure IoT Cloud, on all other information we will just send you a bit later, okay?
Thank you. Sure. Yeah, regarding like overall what we usually try to do, so when we consider like for LoRa Microsoft Azure, right? Usually we still try to be, let's say, cloud agnostic, because the thing that, again, this is definitely related to projects which we consider our own investment. Because if we have customers' requests, definitely it's up to the customer which cloud, which infrastructure, which technology to use. But if we speak about our own investment into solutioning some ideas, we try to be, as I mentioned, cloud agnostic, which means yes, we may use, for instance, like Microsoft Azure for this LoRa project, or like AWS for the project related to the first slide when we consider solution to get the data from drones as a monitoring system to analyze it through AI solutions, machine learning. But at the same time, we want to have the flexibility if, for instance, tomorrow, due to any restrictions, constraints, or I don't know, requirements from anybody, we could move it to any other cloud. So that's why we don't have cloud preferences when we consider our own projects. In terms of what AI tools were used, yeah, I need to double check because in general, all this project, as I mentioned, EPAM is big company distributed globally, and in many solutions we involve not just like one team somewhere in one location. We use different teams based on their expertise and availability as well. So regarding exact machine learning AI tools which were used for crop disease identification, yeah, I could double check a bit later.
Iladzao, one last question. One last two questions, in fact. The soil temperature probe that you showed in is that a prototype or is that something you're commercializing?
I didn't hear well the part before like commercializing. So
which one? You had one slide where you had a sensor system for soil and temperature, humidity and temperature, and so is that an existent or is that just a prototype?
I got it. I would say it's more prototype-like because I think I missed it. I didn't mention it, but the idea was it was initially it was part of the contest. So
Okay.
we were participating as a company who supports this contest to design a product solution which is about both components, actually three components: hardware, software, and let's say usability of this solution. So make it easy to use by people who do not have a master's degree in computer science. So, I mean, it was a working solution, but in terms of the future, yeah, I don't think it has like as a commercial product.
Okay. And the same with the greenhouse, it was all prototyping with low-cost components to do that, because it's a difference between, just a question about difference between the cost of your doing prototyping and then the cost of moving that up to an industrial commercial system. Would you be, I guess, who would your target audience be eventually?
This is a great question. Thank you. So for the greenhouse, yes, that's also prototype or just kind of like proof of concept. But with greenhouse, there is big difference in comparison to probably the first solution I mentioned and you asked about. So the greenhouse idea was to have a solution which is cheap in terms of components. And yes, you're right, definitely it's getting more expensive if we considering scaling it to like production ready solution. That's true. But still, to prove that you could use, and as Vasily mentioned and showed on one slide, some really simple components which you can buy or get from disassembling some, I don't know, old car, for instance, right? So that was number one, because many speakers today mentioned that the one of biggest issue for agriculture, right? Especially countries which do not have like financial wealth, and it's much more complicated for them to introduce and implement smart solutions because usually they're expensive. I mean, if you don't have proper support. So that's number one, make it cheap. Number two, the idea was from software part to have it easily distributable through like Linux package. So technically, again, you kind of like get the set of details if you want to try it locally. But if you consider to extend it, yeah, definitely you need to have some team of experts. When I say team, it's not exactly something very big in terms of headcount, but yep, I would say you need some experts to be onboarded to help to scale it. And Vasily, do you have anything to add, or Konstantin?
Actually, I do have. So our main business is to create something which is ready for production. We have all necessary expertise, like in supply chain and manufacturing, logistics, and how to scale. So we work directly with our clients when necessary to consult regarding upscaling, regarding how to make it possible and how to make it as cheap as possible. Because initial stages of prototyping are usually quite expensive, or R&D even more expensive, and then you need to define how you organize all that production, and we help our clients with that. So, but as Vlad mentioned, those are like, we are trying different technologies, and we have semi-ready solutions. As soon as we feel that we have demand, we have something to offer to the market, basically. So this is our approach here, especially regarding hardware and embed. And Max, you wanted to add something?
Yeah, I just wanted to add slightly about the hardware part of it. We have the but a lot of professionals related to the hardware design. I mean, electrical engineering and mechanical engineering, and we can create the custom solution starting from the board. I mean, of course, for the prototyping phase, it will be off-the-shelf part, but for the pre-production alpha or beta version of the device, it will be a fully customized solution that we can not only manufacture right here, we can provide necessary documentation and everything that's involved there. So in terms of getting closer to the production, it will be a fully custom solution.
Thank you. Thank you very much. So now we will, maybe you have, no, it's okay. Okay, perfect. So thank you again. All of you from EPAM Systems, really thank you.